Well, thanks a lot, James, and thanks everyone for coming along. It's really great to be able to come before you today and to tell you a bit about the work we did and what we achieved in the Stavely project. Like James said, it's coming to a conclusion now, so we're able to actually present a lot of our findings, which is not a situation I find myself in a lot of the time whenever I give presentations. Before I start, this photo here is a photo taken from the top of Mount Dryden looking out towards the Grampians Ranges. And this is one of the very few places that rocks of the Stavely Arc are exposed at the surface. And I can remember being on top of this mountain in 2004, I think it is, as part of a uni field trip. And I couldn't have cared less. It was late in the day and I think I just wanted to go and have a beer back at the accommodation. But I found myself back there nearly 10 years later and with a different perspective and much more interested. So hopefully today I can share some of that with you. But of course I'm, I guess in some ways, just the front man for the project. A lot of the results I'll be presenting today have been the work of a really quite a large team. So the project is a collaboration between us and the Victorian Geological Survey, and the key players are there. But I guess as well as the science crew, there's a lot of other people I want to acknowledge. So lots and lots of companies that helped us out with access to drill core, Osco, a few universities, South Australian Survey helped with hire logging, so lots and lots of helpers along the way, and including so many of you who came out and sat on a drill rig or cut up sonic sausages or helped in a number of ways. So we couldn't have done it without the rest of GA. So I just wanted to begin with this slide. If you're anything like me, you've probably seen it a million times, including last week. But the reason why we've seen it so many times is because it tells a really important story. And there's two main things I think that are worth pointing out from it. The first is this green line here, which shows the vast importance of Australia's mineral resources to our national export dollars. The second point to show is these blue bars through here, which show our discovery rate of deposits through time. And if you have a look at it, there's a general trend of decreasing discovery rate, in particular for the giant and the major discoveries. And it doesn't take a genius to figure out that without the discoveries to mine, then you can't have all this export value. So that's kind of what we're on about. And perhaps the reason for the declining discovery rate is illustrated by this map here. So effectively what you have here is in coloured, the dots are known deposits and prospects. The coloured polygons are basically outcropping basement geology, and the rest is cover. And you can see that there's almost a one-to-one correlation between known deposits and where the rocks stick out of the ground. And so why is that? Is it that the covered areas of Australia just don't have any inherent mineral potential? Well, probably not. In some instances we can see the exact same stratigraphy going undercover. Other areas we just haven't properly tested. So these represent areas of really great potential. And really the future pipeline of Australia's mineral resources is going to come from these kind of areas. But it's a real challenge, and we have to address it and get real with it. So one of the ways that we're doing that is through the Uncover initiative, which is really about unlocking the mineral, particularly the greenfields mineral potential of Australia in these covered regions. And I think what it's all about is pretty well summarised by this quote down at the bottom here, which comes from the Uncover Roadmap document. So it's really about delivering Australia's new mines by locating and unlocking future mineral wealth and positioning Australia as a global leader in exploration beneath post-mineral cover rocks. And I think that's a really nice definition, but actually I think there's an even better one, and this one comes courtesy of Googling Uncover, a definition of Uncover. So in particular that second one there, so what I really think it's about is discovering something previously secret or unknown, and some of these synonyms are great. So what we're really trying to do in the Stavely project and other Uncover projects is to detect and discover and root out new mineralisation. So one of the tools that we can use as part of this initiative and part of this this task is pre-competitive stratigraphic drilling. So this is identified in the National Mineral Exploration Strategy, as well as that Uncover Roadmap document as a key priority area. And what we're trying to do with these kind of projects is to acquire and deliver new pre-competitive data which will help us to understand the mineral potential undercover. But I want to point out that even though this talk revolves a lot around drilling, it's really just a tool to solve the kind of problems we're after. The fact is the rocks don't stick out the surface, so we can't go and hack it off with a hammer like, you know, maybe they would back in the oldie day, and we need a drill rig to effectively operate as our hammer. So the real, I guess the real guts of these projects is in the science thinking and the integration of a whole lot of pre-competitive data which goes into them. Okay, so why are we doing it? Why is GA involved in it? Why are the states involved in it as opposed to industry? And that's because we have different aims. So what we're really after as an overarching goal is to help reduce the technical exploration risk to explorers by providing the overall geological context for explorers. So there's a few things involved in that. Characterising geophysical domains, so basically solid geology interpretations with real rocks. Testing geological models and concepts that all of us love to draw cartoons and wave our arms around, but we want to be able to test those models to see how right or how wrong we are. To constrain how deep it is down to the rocks, so cover thickness models. And finally, to identify proxies for mineral system processes. So trying to pick up the geological drivers of mineralisation, which is maybe a bit different from what someone in the mineral exploration industry might do, trying to specifically hit an ore body, which is not quite what we want to do, but we wouldn't complain. So this is the first regional drilling project that we undertook was the Stavely project, which I'm talking about today. And this is really the first onshore hard rock stratigraphic drilling program for a very long time. We've been involved here at GA in other stratigraphic drilling programs, particularly around groundwater and things like that. But this is trying to get into basement. And I tried having a bit of a trawl around on the intranet for the last reference I could find to stratigraphic drilling by GA or AGSO or BMR or whatever iteration I could find. And this was the best I could come up with. So this is a record from 1990, but actually the hole was drilled, was completed in 1988. So it's been a really long time. So basically what happened in 2012, the National Mineral Exploration Strategy was released, and like I said, that flagged stratigraphic drilling as a critical source of information to help unlock the cover challenge. And I guess related to that, coming out of it, GA was given ongoing funding for pre-competitive data acquisition, and this included money for stratigraphic drilling. So following on from that, in 2013, we had some consultation with the states, and that led to us establishing the Stavely project with the Geological Survey of Victoria, and we've been going since then. So because we're reaching the end of the project, we're able to actually give some of our key achievements, and this is what I think are kind of the big ticket items. There's a few others I could mention, but these are the things I guess I'm most proud of. So firstly, we've been able to identify undercover a large Cambrian arc system. So I'll be talking about all these more in detail later on, but we've also been able to establish the geological and temporal context for mineralisation. And this has led to us greatly expanding the search space for a whole range of arc-related mineral systems, in particular copper porphyry, but also things like VHMS and epithermal mineral systems. And finally, this place has been absolutely smashed since the Cambrian when the arc was active, and so we've been able to, using structural geology, to unravel that post-Cambrian history. So in terms of the regional setting, this is there a laser pointer here? Maybe not. Never mind. In terms of the regional setting of where we're at, this is the project area. It sits in Western Victoria in the Grampian Stavely zone. But in the broader context of Eastern Australia geodynamics, It's right on the eastern margin here of the Cambrian-Delamerian origin. So this is a generalised geology of the area. This is the surface geology map. That's a stratigraphic column. I'm not going to get into in great detail because the rocks that we're most interested in are these ones, the Mount Stavely volcanic complex, and they occur in three main belts which outcrop. So in the Stavely belt in the south, in the Black Range in the north, and in the Dryden belt, which is sitting out to the east of the Grampians, where that photo I showed you was from. Overall, if we do a sort of quick and dirty back of the envelope calculation, they comprise about 0.5% of the rocks that are exposed at the surface in this project area. This is what they look like in outcrop. Volcanic breccias, most of them are volcaniclastics, but some lavas. This is a rhyolitic lava actually from a drill hole. But even though this outcrop map might look a little bit grim, the situation is considerably more dire. So this is a photo from Dave Taylor from GSV, and this is, believe it or not, one of the key type localities for one of the major formations in the Mount Stavely volcanic complex. So, if you sort of squint, you can see a little bit of rubble there. So, it's not fantastic outcrop. To get any real information out of this area, we really need to drill. And maybe because the outcrop is so shabby, there's been a lot of debate over time about these rocks and how they formed. So the first reference to them is in the late 1870s, when a guy was going around and he was mapping the Grampians. He went, oh, hang on, there's some volcanic rocks here. But it didn't really move on very far from there until almost 100 years later, when Tony Crawford and others were working in the area and doing a lot of geochemistry and petrology and things like that. And they interpreted these volcanic rocks largely from outcrop as parts of a magmatic arc system, which they referred to as the Stavely arc, and which I'll be calling it for the rest of the talk. From there, in the mid-80s, the Mount Stavely volcanic complex was formally defined by the Victorian Survey. But then we kind of start to go off the rails a little bit. So in the early to mid-90s, I guess, coming out of work in Western Tasmania and drawing parallels with the Mount Reid volcanics there, the Stavely arc rocks were interpreted as maybe part of an analogous setting to those, so post-collisional extension-related volcanics. Then there's some other sort of exotic interpretations. So a lot of the magnetic rocks undercover, which I'll show you shortly, were interpreted as part of a seaward dipping reflector package related to passive margin formation during the breakup of Rodinia. So that's something different again. And then more recently, it seems like everything old is new again, and people have started to think of this area as maybe a magmatic arc setting again. But there's still a lot of discussion and a lot of controversy. So, if we are to think of it as a magmatic arc, what might it look like? So this is an example sort of close to home. This is Indonesia, where we're subducting underneath the plate there and causing all sorts of volcanoes and things. But maybe an example that's a bit more spectacular and you might be more familiar with is the Andes in South America, where the Pacific plate is going underneath South America and causing a massive belt of volcanoes and mountain ranges and things like that. But, who cares, right? Well, this is why we should care. This is a copper mine in Chile, and this is just enormous, right? Like, I haven't got a scale on there, but it's something like 4 kilometres long. It's 850 metres deep. It's a massive mine. So, these kind of deposits form in these kind of geological settings. And if we can find something like this in, humble Western Victoria, that's a real game changer for not only the economy of that state, but also for Australia. So, returning to our area, happily, we do have some known examples of mineralisation which have come about from sort of on and off exploration over time. We have examples of all those arc-related mineral systems, so copper porphyry, epithermal, volcanic hosted massive sulfide prospects. And those occur largely in the Stavely belt, which is the best exposed belt, but also we have examples from the other belts there. And so there's a spatial association there. I'll talk a little bit more later on about what the genetic link might be. Yeah, we'll move on from there. As I mentioned earlier, cover is a real issue in this area, and I suppose in here we have a bit of a loose definition of cover, so it's not quite what you would usually think of unconsolidated sediments and sands and things like that. For us, cover is anything after the Cambrian, so it includes things like the Silurian Grampians group, which is actually a rock and what forms the Grampians ranges. We have other rocks that are cover as well, so the Devonian Rocklands volcanic group, we have Permian glacial deposits, we have sediments from the Otway Basin, the Murray Basin, and then over the top of that, just for fun, we have the recent basalt flows of the newer volcanic group, which cover a lot of the south of the area and really aren't very helpful to us when it comes to looking at the magnetics. But that's all right, they look fairly spectacular. So I guess having a look at the past history there, what we know about it, what we don't know, we can come up with a few key questions. So the first question is, when you have a look at this magnetic picture here, we don't know what a lot of these magnetic rocks are. So what are they? What are the rocks? What's the setting they formed in? Are they arc related or are they something completely different? We want to know what the age of the mineralization is and which rock packages correspond to key metallogenic events, so then we can hunt other ones down. And finally, since it's all been chopped up since the Cambrian, we want to know how all these different magnetic belts you can see all over the shop, how they fit back together into a coherent picture and how we can understand a bit more what's going on with the structure in the area. So this is the first question I'm going to look at. We're going to have a look at what the basement rocks are and what their characteristics are. So to do that, we need a sample, and that's where drilling comes into it. So with the Stavely project, we drilled 14 fully cored stratigraphic drill holes, so coring from surface right down through to basement. And that took 147 days. We operated on a single shift basis, so it took a little bit longer than maybe it could have if we went double shift, but we want to keep logistics under control, and there's a lot of farms and things around there. We don't want to cause too much noise pollution. So we finished that up in September 2014. And that was done using two different drilling methods. So we used sonic drilling to get through the cover because it gave us the best penetration rates and the best core recovery. And you can see up the top image there, that's a little bit of core that came out of the sonic drill rig. And you can see all these beautiful shells and all that kind of thing. And it's just fantastic textures we can see that you wouldn't see otherwise if we would have gone through it with say mud rotary or something like that. And then we finished it up with diamond drilling tails. So there's an example of the diamond core there. So what that resulted in was about 2.7 kilometres of drill core, of which 400 metres, was funded by the University of Melbourne, so they could set up a geothermal monitoring bore. And all that cost us 1.6 million. So not bad considering we filled in the picture quite considerably. I won't be going into it in any real detail in this talk, but I do want to mention that drilling was done in partnership with the Deep Exploration Technology CRC, and that was a really great collaboration that let us have access to a bunch of DET CRC equipment that they're developing, like the Labbit rig and the AutoSonde and things like that, if people are familiar with it, and it added a lot to the project, but maybe that's something for another talk. So in terms of what we were trying to achieve with these drill holes, well, there's 14 holes, but really we can break it down into maybe five key drill hole aims. So the first set of holes were really targeted around testing undercover extensions to the Mount Stavely belt. So the Stavely belt is, like I said, it's the one that we understand the most. It's the one that has the most known mineralisation associated with it. And so any extensions to that undercover are kind of quick wins. It's got all sorts of sediments and volcanics over the top. So we're testing some of that. We had a group of holes aimed to test the eastern margin of the arc, because that's going to then define what your exploration what we refer to as the fairway, so I guess the go zone for where you might find deposits is. Similar to that, we had a few holes aimed at testing the western margin, so that was largely based on structural interpretations by the GSV, so we wanted to test some of those interpretations in that area and pick up where the arc ended in the west. And the majority of holes were aimed to basically plug a hole into some of these magnetic features that we could see to say, well, what are they? You know, are they bits of arc? Are they bits of passive margin? You know, what are they? And then finally, we had one hole which was, I guess, aimed at sort of coming up with some criteria that explorers could use in the area. So we thought we could recognise a geophysical signature which might have been as a result of a mineral system. So we wanted to characterise that response and see what was causing it. So that was the aims, and so then we went out and drilled those holes. And drilling's a lot of fun. You get to go around and there's big trucks and, you know, it's a lot of fun. You get to see rocks coming out of the ground for the first time and, you know, and lick them and do it. Well, we're not allowed to lick them anymore, but, and also they're covered in all sorts of stuff, so maybe not the best idea. But it was great. Like, you know, nothing beats getting a rock out of the ground for the first time and going, aha, that's what that is. But it's also not a lot of fun at times. So Western Victoria in winter isn't maybe the most pleasant place to be. Some very cold mornings, some very slushy ground conditions. And so, you know, there is another facet to it, and that is the operational and logistics side, which is, you know, not trivial, right? You know, you don't want to be stuck in this paddock when it buckets down and you've got to drag your rig out with a bulldozer. Oh, we had to do that a couple of times, actually. So before I move on to talk about the basement rocks, I just want to talk about the cover because, you know, it is part of the Uncover initiative and we do want to understand what the character and the depth of cover is. So in the area, we got to basement in all our holes, which was great because we could actually say what cover depth there was. So typically less than 150 metres, so very, very accessible. And I won't talk about it here. Other people have spoken about it in presentations at GA previously. But we did a bunch of pre-drilling geophysics to try and predict where that basement cover interface was. And what we found by and large is that we had pretty good agreement between what our model depths were and what the actual depths were. So that kind of work is then being fed into, I guess, what we can tell explorers for the region. If you use passive seismic or something like that, you know, you can reasonably predict how deep you're going to need to drill. Okay, but what I'm going to be focusing on is the rocks. So in a lot of holes, we got what we were after. Dominantly intermediate to felsic volcanics. The top image there is a volcanic breccia, really beautiful sort of textures. Lots and lots of volcaniclastics, coherent lavas, some coherent basalts there. We also drilled a bunch of sediments, which I guess we were hoping might be volcanics, but that's okay. They also tell us a lot of useful information. So turbidites of the Glen Thompson sandstone. And there was a few other surprises in there. So this hole down here in the south drilled very close to the Stavely belt. We were aiming to pick up the contact between the turbidites and the volcanic package, and accidentally jagged a bunch of porphyry dikes, intruding the sandstone there with some associated alteration mineralisation. So that was great because that gave us another, I guess, string to our bow to study. So there's a bunch of tools that we can use when we want to try and understand the region. So these are the tools that we applied to the area. So lots of geochemistry, isotopes, geochronology, hyperspectral characterization, rock properties, both on the core and downhole geophysics, as well as that, a lot of geophysical interpretation and structural geology. But what I'm going to talk about for characterizing the basement rocks is geochemistry, because it's really a geochemical story. And that's because different rocks formed in different tectonic settings are going to have fundamentally different geochemistry reflecting the sources that they come from. So this is kind of the scenario that we think might be what's in the Stavely area. You know, this is based very much on the Andes, so you've got a subducting slab, an arc and a back arc. So if we have a look in at the arc, this has some diagnostic geochemical properties. So melting in these areas is facilitated by dehydration of the subducting slab, and you've got little bits and pieces of fluid coming up here which cause melting in the mantle wedge. So what you have is high concentrations of fluid mobile elements, and then those elements are enriched relative to the more immobile elements, so the high field strengths and the rare earths. And as well as that, we developed this classic sort of subduction signature, so negative anomalies for niobium and titanium. And this is the kind of thing I'm talking about. So this is data that an average for rocks for part of an average for part of the Andes, and you can see a lot of those features I was talking about. So these elements it's a diagram normalized to primitive mantle, which is one of the things we can normalize it to, and it's arranged in order from you've got the most compatible elements through to incompatible here. The fluid mobile elements are these ones in green, large iron lithophile elements, so cesium, rubidium, barium, all those kind of good things. And those are enriched relative to the blue elements and the red elements, so you get a nice slope like this. And as well as that, you've got the niobium, negative niobium anomaly here, negative titanium anomaly. So if we go and have a look at maybe another setting, mid-ocean ridge basalt, you can see it's fundamentally different. And that's because there's fundamentally different processes going on. So this is an extensional centre. You're accessing a depleted mantle source, no subduction input. So you've got depleted geochemistry, so all these incompatible elements are lower than these ones. You don't have that enrichment in fluid mobile elements. You don't have a well-developed niobium or titanium anomaly. So we can use this kind of understanding to understand the rocks that we got in drill core in Stavely. So this is some of the data from the igneous rocks. So again, I've plotted them on the same diagram here. And what we can see is all those kind of arc-related features. So again, enrichment in the fluid mobile elements to the non-mobile ones, niobium, titanium, all the things we want to see. So that's great. Our hypothesis was proven, except maybe for this one here, which something funny is going on with it. We need to understand it a bit better, but it doesn't look to be part of the same package. So what I've shown here in green is the drill holes where we have arc rocks intersected undercover, and this is kind of the first instance where we've been able to identify these. Other drilling programs have identified them elsewhere, but these are the first ones into these particular regions that we can say, yep, we've got it. But maybe it's not quite as simple as that. So again, this is the data from the Andes, which we know is an arc because it's cranking along today. And what we can see is that when we plot average upper continental crust, it looks pretty much exactly the same thing. So I guess one question is, well, do we have something like a mid-ocean ridge basalt which has just been contaminated by upper continental crust, giving us sort of like a false subduction signature? But luckily, geochemistry to the rescue again. So there's another plot we can use. This is niobium versus thorium normalized over ytterbium plot. And there's a few cool things it can tell us. So you can see here this grey band is the Morbaray. So mid-ocean ridge basalts and I guess non-subduction related rocks are going to all line up along there. So this is some data from real mid-ocean ridge basalts. You can see it's a very tightly defined band. In contrast, if for arc rocks, I've plotted a series of them there. I've just taken the data from a compilation on the internet, and you can see that they systematically plot above that Morb array, and they plot in their own arc array. So subduction is going to displace those rocks to above that line. Whereas on the other hand, if we have, say, a mid-ocean ridge basalt, which is contaminated by upper continental crust, we'll form a trend going from somewhere in that grey area, diagonal up, trending towards upper continental crust. So we'd be able to detect that kind of process going on. When we plot our Stavely rocks, this is where they sit. They plot in the arc array. Okay, this one's a little bit, I've lost my mouse. This one's a little bit different. We need to do a bit of work on that. But by and large, what we can see is there is no mixing trend there. They plot in the arc array, they evolve along this sort of parallel trend, so we can confidently say that they are more than likely emplaced in a magmatic arc setting. So what does this all mean? Basically, what we've been able to do is go from the really measly exposures in the known outcropping belts and really increase our known distribution of these Stavely arc rocks under cover. As well as that, we're able to say something about the tectonic settings. So the rocks have characteristics similar to some island arcs, like the Philippines maybe, that have a bit of continental material involved, or perhaps a continental margin arc setting similar to what you see in the Andes today. And this setting is favourable for forming some of these large mineral systems which I was talking about at the start. So that's a big tick for prospectivity in the area. So having answered that question, let's move on to the next one, which is around the age of mineralisation and what kind of rocks it's associated with. So we know that there's a spatial relationship between mineralisation in the area and the outcropping rocks, but what we want to know is, well, is there also a genetic link? And if there is, are there multiple phases of mineralisation, or is it part of the one single event? So again, if we rummage into our toolkit, we can come up with geochronology, which is our tool of choice for solving this. Before we began this project, there was a bit of geochronology in the area. This is showing, I should say, sorry, that all this is Chris Lewis's work, who did all this dating and put this sort of story together. But this is the information that occurred before we went in. And what you can see is it's not a lot, first of all, but then when you delve into a little bit deeper, there's a mix of techniques in there. So there's uranium, lead, zircon, there's argon, there's a lot of different techniques mixed in here. There's a lot of different vintages of labs and standards used. So basically what that results in is a fairly broad spread of ages and a lot of imprecision. So as part of the project, we acquired 23 new uranium, lead, shrimp, zircon ages. That was predominantly done by Chris. We sampled all of the representative lithologies in the area, so not just the volcanics, but also some of the porphyries, the intrusives, sandstones. A lot of these samples came from re-looking at historic material, which we had in-house, or which we were able to access from, say, universities. But what we did find is, particularly for our new drilling rocks, a lot of them were really uncooperative. So I guess in some senses that's not unexpected. Most of the rocks we got were sort of fine-grained, intermediate, mafic, volcanic kind of things. You wouldn't expect those to cough up a lot of zircon, and in fact they didn't. So it's quite likely that the actual age range that we've been able to produce is undersampling the real range, but until we go in there and drill more holes and get more material, it's probably likely to stay that way. So this is the new data against the old stuff, and first of all you can see there's a lot of new information here. Not only ages from the Mount Stavely volcanic complex, but also, like I said, the porphyries, the Bushy Creek igneous complex, and so we've got a much better picture of the age in here. You might see that this bit on the end is censored here. It is for now, but not for long. A bit of suspense is always good. So what we're able to do is to define the extent of Stavely arc magmatism. Whoopsie daisy, sorry. So it occurs between, roughly 510 and 498 million years. So we're able to, bang, we've pinned that event. But what about mineralisation? So what we're able to do here is go to some of the industry drill core, which was held by some companies in the area, but also sitting in the Victorian Geological Survey drill core library. And we were able to get out of there molybdenites, which we would date with the rhenium-osmium method at ANU. And so the ages we get out of that are sort of, 510, 500, 503, that sort of range. We also tried to date some of the volcanic hosted massive sulfide mineralisation by dating the host rock, which is syngenetic with the mineralisation. We can tell that from the textures. And again, that returned an age of about 502 million years. So now that we've uncensored that data, you can see it all together there. And what we're able to really say is that the Stavely arc magmatism and mineralisation are all part of one single event, as best as we can tell. And so the implication of that is that mineralisation could and probably should occur in other rocks of the Stavely arc that we've been able to identify. Okay, so moving on to our final question, which is how do the structurally dismembered magnetic belts relate? So this is the big post-Cambrian mess that we've inherited. These are the different belts of rocks. You can see that they're going in all sorts of directions. You know, some of them are doing really, cocoa bananas things, like this orange one up here, which is sort of, looks a bit like a fork. You've got things going this way, things going this way. It's just a big mess, right? So the tool that we use for this, when we go back into our toolkit, is structural restoration. And the real key to being able to do this comes out of some work that the Victorian Geological Survey has done. So this is a photo that I took of the Escondida fault, which is a fault in the area in Glen Thompson sandstone. And when we have a look at that in a bit more detail and study the structures, we can recognise strike slip movement around here. And we know that the age of this is after the Cambrian, because these rocks are Cambrian and they've been dismembered afterwards. So we're able to recognise that strike slip deformation at an outcrop scale. When we broaden our view to the regional scale, this is gravity data, and we can again see a series of these strike slip faults offsetting the stratigraphy in the area. So we can see at all scales, outcrop to regional scale. And so using this understanding of the effect of this post-Cambrian strike slip deformation, we need to get in our time machine and go back and undo it. So this is work from Ross Cayley. So we're going to unwind using what we know about the structure to restore it back to what it looked like originally. So this is the mess we have before us at the moment. And what we can do, we can gradually undo it, strike slip deformations getting undone, until we reach the point where it represents what it looked like back in the Cambrian. So three broadly parallel northish trending belts of arc rocks. This is what we have today. Like I said, it's a big mess, it's all chopped up, we have mineralisation associated with it. When we restore it, it's a much more sensible pattern, and we can get the proper original context of that mineralisation. So what? Well, so what is that all of these belts, all of these big three that we've been able to restore, have some known mineralisation associated at the surface. I haven't shown it for this middle one, but you'll have to trust me on that. Therefore, since we know some portions of the belt have this mineral potential, we would say that the potential extends across the length of these belts. And in a lot of instances, it's quite significant. So the western belt there has a strike length, once we restore it, of 235 Ks. The middle belt there, 382 kilometres. And then the big boy over in the east, 542 kilometres. So there's massive amounts of strike length of what we think is prospective stratigraphy. So we've been able to answer that question. So we've looked at all three. Let's revisit the controversy that we had at the start. So as we saw, lots and lots of different models proposed. Really not a holistic understanding of what the rocks are undercover. So what can we say? Well, we've kind of been down the garden path a little bit, but we can say three key things. Firstly, that there are vast tracts of Cambrian arc rocks which occur beneath what is quite shallow cover across the region. Secondly, we can say definitively that magmatism as part of the Stavely arc and mineralisation were part of the same event, and therefore should be associated one with the other. And thirdly, the big post-Cambrian mess can be restored. So what that tells us is that these restored belts, which have massive strike lengths, are prospective in all their now dissected bits. So we have the confidence to actually target some of these belts where there's no known mineralisation. Those are kind of the big three. Of course, there's lots of other activity which has gone on as part of the project. I just want to give a bit of a shout out to that. Like I mentioned at the start, there was benchmarking of geophysical methods for determining depth to basement. We established the burial history of the area through some studies, and this is some of the work from Dave Taylor around that, which is looking at, these deposits form at high crustal levels. Who's to say since the Cambrian they haven't been eroded and are somewhere sitting in Bass Strait at the moment? So we think they should still be there in place, ready to be found. As well as that, we've done detailed mineral system investigations, lots of stable isotope work, lots of petrography, things like that. And some work around trying to detect the distal footprints of buried mineralisation. So conducting geochemical transects across what we know is there, to try and see what methods might be able to be used by explorers looking for blind mineralisation. So I guess, if you're going to think of a money shot, this is really it. So what we did with this project, we acquired a whole lot of new pre-competitive data. This has led to us understanding in vastly more detail the distribution of Stavely arc rocks in the subsurface. And this has greatly expanded what we know of the search space for these arc-related mineral systems, predominantly copper porphyry, because those are the big guys, but also other systems which are well worth following up, epithermal, VMS, things like that. And so basically what this has led to is what we believe is a new undercover minerals province. So loads of real estate just waiting for renewed exploration efforts there. So those, I guess, are the key results, and like I said, we're at the end of the project now, so I can kind of, look back misty-eyed on what our experience has been. So I think there's a few important lessons that we've been able to learn along the way. And the first of that is the importance of having a really good team. This is some of the crew logging drill core down in Werribee from our project, or at least they're looking busy. It's so important to get the buy-in from these guys. They're all super interested, actually cared about what the project was going to achieve, curious, wanted to do new things, cool new science. So, you can't underestimate the importance of having a good team. And I guess the skills mix in that group really added to the project. We got geochronologists and spectral geologists, economic geologists, geochemists, all these different skills. And by integrating that range of science, we're able to say a lot more than we could than if it was, say, a smaller or more homogeneous team. The next point is that real rocks are required to make a real difference. So I guess we can draw lines on a map as much as we want from geophysical data. But if you actually want to say something about that area and you want to give explorers the confidence to go in there and have a look, what you need is a real chunk of rock that you can say, that's what it is. And finally, and I think it's sometimes the forgotten aspect of these kind of projects, is that the logistics and the operational constraints, they're a major factor. They don't just happen by accident. For Stavely, we were lucky to have Tim on board, and he had a lot of wise words and experience which he could bring to this, and it would have been a real struggle without him. So, it's something that is a real factor. So, just to close off, I wanted to have a think about what this might mean for where we move in the future. So at the beginning, I showed this map here, and yeah, it's a really daunting picture, We don't know a lot about these covered areas. We don't know much about the geology, we don't know much about the mineral potential. But really, it's no different here. We have some outcrop, some mineralisation associated with that outcrop, but loads and loads of cover, but we can have a look at those rocks. So this, what we applied to the Stavely area, we can also apply across the rest of Australia to look at this, this Greenfields exploration challenge. So in terms of future directions, like I said, these tools that we've developed as part of the Stavely project, these can help us to achieve the aims of the Uncover initiative. So we'll be rolling out this kind of workflow and methodology as part of the Exploring for the Future initiative, which you would have heard about last week. So we have two regional study areas as part of that. The Isa-Tennant area with the Northern Territory Geological Survey and the Geological Survey of Queensland, and the Kumpana area in South Australia, which is going to be done in collaboration with the Geological Survey of South Australia. Another future direction, which is really in its infancy, but I think is quite an exciting area, is the idea of a national onshore drilling initiative. So this is flagged in the Uncover roadmap as something worth pursuing, and there's been a little bit of traction there. But this kind of approach to understanding what the rocks are, and then maybe infilling with faster and cheaper drilling techniques, but maybe that give you less of a not quite a rock as a sample, maybe more like something like a powder, but having that understanding of what the rocks are through this kind of work can help us to interpret that and really understand vast tracts of Australia that we just don't know very much about. So thank you very much for coming along and listening. It's been, like I said, it's been a great project, and it's been really great to be able to share some of those results with you. And so hopefully, the road is open to this area being opened up for exploration. Thanks.
So thank you, Anthony, for an excellent talk, a very clear expose on behalf of the team. Obviously really good science. What I particularly liked about it is it went beyond documenting what the rock types are and through to prediction of what it might mean for mineral potential, and that's exactly what GA should be doing in this space. Do we have any questions for Anthony? Yes.
I had the impression from the geochronology that arc was quite short-lived. Is that a realistic impression, or is that more a reflection of how much of the basement you actually drilled?
It's hard to say about the first thing. We can tell from the stratigraphy from part of exposed parts that there are the lower parts of the stratigraphy are things like bonanites, and there's some arctholiites and things like that in there, which we can't date because they're zirconless. So those potentially represent older phases, and we probably expect there to be older phases. From looking at the geodynamics more broadly, we think that maybe the arc had its origins around about 520 million years. So we expect it to probably be longer lived. That said, all we can deal with is the data we have, right? So all it tells us is that it was about 10 million years. But definitely maybe revisiting some of these more mafic phases and maybe trying to have a look at some other minerals that we can date. That might be an avenue for future work. But, our time's done.
Other questions? Yes, Russell.
Yeah, thanks, Anthony. You've actually been able to distinguish your three belts and put them into back into a linear progression.
Yep.
What characteristics of various patches of rocks enabled you to put into one belt or the next? In other words, what was the geochemical and age differences between the three belts?
Yeah, sure.
To allow you to distinguish between them.
Yeah, sure. That's an important point. So we weren't able to correlate much with age because of the lack of ages that we were able to get. But there are there's some quite strong geochemical links between the exposed portions and some of the belts undercover. So it all sort of fits together. It's largely a structural story, but it sort of checks out with the other data that we have.
Just a follow-up question then. What's the actual width? When you do the reconstruction, you didn't have a horizontal scale, so what's the width of the arc belt with the three of them together?
That's true. The thing's probably been squashed up quite a bit as well during the Delamerian. So that configuration is actually not the original. It's not the original arc. It's after the Delamerians come in and sort of squashed everything to begin with, and those are sort of like different slices related to that deformation. The original width, I can't tell you off the top of my head, sorry. Ross has some ideas, and we're reporting it, but I can't remember.
Just one more question. With your three belts, what's the actual rock types that were in between them at that time when they came in?
Oh. Well, what? Good question. Jeez, Russell.
Fertile ground for future work, I guess.
Yeah, well, I mean, like I said, those three belts are the result of, I guess, it's after the Delamerian. So it's probably more likely to be between them slices of, or pretty large tracts of those Cambrian turbidites, so Glen Thompson sandstone and things like that, Nargoon group. But we expect the arc rocks to be there beneath that, I guess, cover in some senses.
I'll take one last question down the way.
Right, cool. Thanks, Anthony. It's early days yet, but have you seen any response from industry to this new pre-competitive data?
Yes. Like you said, it is very early days, and when we finally deliver our final report, we are planning on having a sort of like a industry workshop, and then we'll really see the fruits of this work. But the Victorian government have a sort of a co-investment kind of scheme going on, and there are companies in the area that have been awarded, I guess, some of those co-investment grants, and they've cited this kind of work as part of the reason why they're interested in the area. So I guess we got those preliminary sniffs of people taking up results, but to be honest, our experience shows that this kind of pre-competitive work, sometimes it can be decade or more before you really see the impact it's had.
Okay, we'll have to wrap it up there. Before I let you go, I'll just put in a plug for next week's talk, which is also coming from the Resources Division. It's around the CO2 storage assessment in the offshore Browse Basin, but the implications from that work for petroleum prospectivity. But can you join me again in thanking Anthony for an excellent, distinguished 3 hours?